A speaker emits 45 joules of energy. Okay, that's the energy that's emitted every second, so that's the delta E when the time is 1 second, producing 250 hertz sound waves. That's hertz, so it's frequency. The sound waves travel through the air at 330. That's the speed of sound. That's the speed of the wave. So I'll use c here instead of v. A person is standing 4 meters from the speaker. That's the distance the sound travels to get to the person. But here's the thing. Let's imagine this is the speaker, and maybe it's on a stage, and there's a rock band, playing their guitar. Let's see if I can draw a guitar. You need one hand up here holding the neck. Maybe it's a banjo, not a guitar. Looks more like a banjo or a sitar. And here's the person in the crowd standing, how far is it? 4 meters away from the speaker. Look at that banjo player go. She is phenomenal. Okay, determine the intensity of the sound wave that it's reaching with the person. Well, when the wave spreads out, it doesn't just travel toward the person. Waves, we know, are spherical. They go in all directions. So if it's traveling 4 meters to the person, well, it's traveling 4 meters in every direction. The wave spreads as a sphere. So 4 meters is not only the distance that the wave has traveled to get to her, the listener. This 4 meters is also the radius of that sound sphere. It's like this. The waves are traveling out in all directions, and so they form a sphere. Now this is looking at outer space. Just pretend for a moment that this would be air. Instead of having, in outer space, there is no air, so what you want to really imagine is like these compressions in the air, and instead of going straight across, they sort of wrap around. Those compressions are curved, and they curve all the way around the source here in the middle, which in our case is the speaker. Okay. Determine the intensity of sound waves reaching the person. Well, I know the equation for intensity. It's power divided by 4 pi r squared. So I just plug in. Power is, wait a second, they didn't give us power, they said the energy and the time, but I know that power is the energy divided by the amount of time. It's the rate at which energy is produced or transferred. So how much energy is produced? How quickly is it produced? You make 45 joules from the speaker. You produced 45 per 1 second. So the power is 45. And I can't remember. What's the unit of power? Watt is the unit of power? Oh, it's the watt. I know you're laughing there at home. Okay, so I plug in my 45 watts. 4 times pi times... What's the r again? Oh yeah, it's just the distance, because it travels 4 in every direction. That's the distance it goes in every direction, forming a sphere of radius 4. Determine the wavelength. Okay, well first I have to calculate, but I'm not going to calculate. Maybe I will. 45 over 4 over pi. Use your pi button. You don't want to do what I'm doing. Over 4 squared, 16. 0.22. So again, we get 0.22, and check out what we've just learned. This is not just 4, it's 4 meters. So I distribute the squaring to the 4, I distribute the squaring to the meters, and my unit is a watt divided by a square meter. It's watts per meter squared. To find the wavelength, we have to use c equals f lambda. We know c, the speed, that's 330. We know f, that's 250. Lambda is my unknown, so you just divide by frequency to solve. For time that it takes to travel from the speaker to the person, we do distance over time. We know the speed again, the speed of the waves, that's 330. The distance the waves are traveling to get to the person, that's the 4 meters. So we can calculate the unknown time. Let's look at 5. Clear this off. Or you know what? Let's look at 6. Because 6 has an extra little twist, a little trick. The intensity of sound waves emitted by a speaker is 16 kilowatts per meter squared. Wait a second. Kilo is equal to 10 to the 3. That's the intensity when standing at 5 meters from the speaker. Okay, that makes more sense. It makes sense. Here's the speaker. Here's the person who is 5 meters away. And if there's another person who's like 25 meters away, well, the sound is way less intense for them. I mean, because the sphere here, the sphere of the sound wave, isn't really so big, so it's pretty dense, you know? That sound is pretty dense. The energy is not being spread out so thin. But by the time the wave reaches this person, look at how huge that energy sphere is. That sound is like barely, you know, you're spreading that energy very, very thin. So the wave is less intense for her. Okay, it makes sense then. This value is going to decrease as the wave spreads. The intensity gets less. Well, how do we find power? We use the wave equation, the intensity equation rather, for spherical waves. We know I, that's going to be 16 times 10 to the 3 for the kilo. Power is the unknown. We have 4 pi. What's R? Oh yeah, it's the distance that the person is standing for. So that's because the wave travels this distance in every direction. We cross-multiply to get our answer. Again, use the button pi. Whoa. What just happened? We have 16, 1, 2, 3, times 4 times 25, which is 5 squared. We get 5.0 times 10 to the 6. That's 1, 2, 3, 4, 5, 6. Again, the unit for power is watts. Assuming the speaker's power doesn't change, find the intensity at 10 meters. Okay. Well, we're doubling the distance from 5 to 10. And you might be thinking, wait a second, intensity is proportional to the inverse square. So if you increase this by 2, you have to decrease this guy by 2 squared because it's inverse and it's the square. So we expect this to go down by 4. We expect the new answer to be 4 kilowatt per meter squared. Let's see. I'll just go ahead and calculate power over 4 pi r squared. For my power, I do the 5.0 ... use the unrounded value. It's this number. R is now 10. And what do we get? Let's do it. Okay, I use this unrounded value. I do divide by 4, divide by 3.14159.265. Use your pi button instead. Divided by 100, 10 squared. Look at that, 4,000. That's exactly what we expected. Another way to say this is 4.0 kilowatts.